Picture this. You walk into your apartment one evening. Something feels off. The door doesn't close as smoothly as it used to. There's a thin crack running along the wall. Maybe it was always there, maybe not. The floor feels slightly uneven, like it's dipping just a little when you step on it. You pause for a second. Then you shrug it off. It's probably nothing. That's exactly what almost everyone says. Now let me ask you something. At what point does a building actually become dangerous? Is it when you see a crack? Is it when the floor starts shaking? Or is it only when the whole thing comes crashing down? Because here's the uncomfortable truth. By the time a building collapses, the problem didn't just start that day. It's been there, growing, quietly, slowly, sometimes for years. Buildings don't just randomly fail. They give signs. But the scary part is, not all signs mean the same thing. Some signs are just annoying, some are warnings, and some mean you're already in serious trouble. The problem is, most people can't tell the difference. A small crack in the wall might look terrifying, but it could be completely harmless. Meanwhile, something that looks totally fine on the surface could be hiding a serious structural issue underneath. So how do engineers figure this out? How do they decide what's safe, what's not, and what's about to go very wrong? Here's the surprising part. When engineers design a building, they are not thinking about 1,000 different things. They are thinking about just two. That's it. Two lines that a building should never cross. The first one is simple. Will it collapse? The second one is just as important, but way less obvious. Can people actually live in it comfortably? That's it. Everything, every calculation, every beam, every column, every piece of steel and concrete comes down to those two questions. Will it stand, and will it feel okay to use? Now you might be thinking, wait, isn't not collapsing the only thing that matters? Not even close. Because a building can be perfectly safe in the sense that it won't fall down and still be completely unacceptable to live in. Imagine your floor bouncing every time someone walks across the room. Imagine cracks constantly appearing in your walls. Imagine doors that won't close, windows that jam, tiles that keep popping up. Technically, the structure might still be holding together, but would you want to live there? Of course not. That's where things start to get interesting. Because from an engineering point of view, not collapsing is actually just the baseline. It's the bare minimum. It's like saying, hey, this plane probably won't fall out of the sky. That's not exactly comforting, right? What engineers are really doing is managing risk. They're drawing invisible lines. On one side of the line, everything is fine. On the other side, things start going wrong. And those lines are not random. They're carefully defined, calculated, and built into every serious design. But here's where most people get it completely wrong. They think a building is either safe or unsafe, like a switch, on or off, black or white. That's not how it works at all. A building can be perfectly fine, slightly uncomfortable, annoying but still safe, or dangerously close to failure. And those are very different situations. If you don't understand the difference, you either panic over nothing, or worse, you ignore something that actually matters. And that's exactly why engineers came up with this idea of limits. Think of it like this. Your body has limits, right? You can walk all day, no problem. You can run for a while, gets tiring. Push harder, and eventually you collapse. Same body, different limits. Buildings work the same way. They don't just go from fine to collapse instantly. They pass through stages, and each stage tells you something about what's going on inside the structure. Now here's the key idea I want you to remember. A building doesn't fail in just one way. It actually has two completely different types of failure. One is obvious. The other one, most people don't even realize exists. And once you see it, you'll never look at buildings the same way again. Because suddenly, things like cracks, vibrations, and weird noises start to mean something. They're not just random anymore. They're signals, clues, warnings, sometimes harmless, sometimes serious. And the entire job of a structural engineer is to understand those signals before it's too late. So, in the next part, we're going to break this idea down in the simplest way possible. No complicated formulas, no textbook definitions, just real-life logic. Because once you understand these two limits, you'll start to see buildings differently. Not just as walls and roofs, but as systems that are constantly balancing right on the edge of what's acceptable. And trust me, that edge is a lot closer than you think.
All right, let's strip this down to something real simple. Forget buildings for a second. Think about your phone. You've probably dropped your phone before, right? Now, there are two very different outcomes when that happens. One, nothing really happens. Maybe a tiny scratch, maybe not even that. You pick it up and keep going. Two, the screen shatters, completely unusable. Game over. That second situation, that's what engineers would call a hard limit. You crossed a line and now the thing is broken. But there's actually another situation in between that people don't think about much. Your phone doesn't break, but it starts acting weird. It overheats, it lags, the battery drains way too fast. Technically, it still works. You can still use it, but it's annoying, frustrating, not the experience you expect. That right there, that middle zone, is the key to understanding everything. Because buildings work exactly the same way. They don't just go from perfect to collapsed. There's a whole range in between where things are still standing, but not really okay. Now, let's bring it back to something even more relatable. Your own body. You can walk all day, no problem. Push a little harder, you start getting tired. Push even harder, your muscles burn, your breathing gets heavy. Keep going, and eventually you collapse. Same body, but clearly there are different limits, right? There's the point where you feel uncomfortable, and there's the point where your body just gives up. Those are two completely different lines. And this is exactly how engineers think about structures. They don't just ask, will it collapse? They also ask, when does it start becoming unacceptable to use? Because those two moments are not the same, not even close. So instead of thinking in black and white, safe or unsafe, engineers think in terms of limits, invisible boundaries, lines you really don't want to cross. The simplest way to understand it is this. A limit is the point where something stops being okay. That's it. No complicated definition, just that. Now here's where it gets interesting. There isn't just one limit, there are two, and they control everything. The first one is obvious. It's the point where the structure can't take it anymore. Too much load, too much stress, something breaks. Beam snaps, column crushes, foundation gives way. Once you cross that line, the structure is no longer doing its job. That's failure in the most dramatic sense. The second limit is quieter. Nothing breaks, nothing collapses, but things start to feel wrong. The floor bends more than it should. Walls start cracking. Doors stop lining up. You feel vibration when someone walks across the room. The structure is still standing, but it's not performing the way people expect. And that matters more than you think. Because buildings are not just supposed to not kill you. They're supposed to be usable, comfortable, reliable. Now here's the part that really changes how you see things. Most of the problems people complain about in buildings are not about collapse. They're about this second limit, the "this feels off" limit, the "why is my floor moving" limit, the "why are there cracks everywhere" limit. And engineers take that just as seriously. Because if you ignore that line, you end up with buildings that are technically safe, but practically terrible. Now, don't get this twisted. These two limits are not equally dangerous. One is about inconvenience, the other is about survival. But both matter, and both have to be controlled. So when an engineer designs a structure, they're constantly checking two things. First, are we anywhere close to breaking something? Second, even if nothing breaks, does it still behave properly? If the answer to either one is no, the design isn't good enough. Simple as that. And here's one more thing most people don't realize. These limits are not based on feelings. They're not guesses. They're defined, calculated, and built into design standards. Engineers don't just hope things will be okay. They calculate where those lines are and then make sure the building stays comfortably on the safe side. That's the whole game. Stay away from the edge, because once you cross it, you don't always get a warning, especially with the first limit. So now that you understand the idea, two limits, two very different kinds of problems, we can finally put names to them. Not the boring textbook way, the real way. The way engineers actually think about them, on site, in design offices, and when things go wrong. And once you see that, you'll start to understand why some issues are just cosmetic and others are a big deal, way bigger than they look.
Now we're getting into the part that actually keeps engineers up at night. This is the serious one, the one that if you get it wrong, people can get hurt, or worse. We're talking about what engineers call the ultimate limit state. But forget the name for a second. Let's say it in plain English. This is the point where the structure can't take it anymore. That's it. Game over. Something breaks, and once it breaks, the whole system can start falling apart. Now here's the first thing you need to understand. Structures don't fail because of one big dramatic moment. They fail because something reaches its limit. A beam bends too much and then suddenly snaps. A column takes too much load and crushes. The ground underneath a foundation can't support the weight and starts to give way. And once one critical part fails, the load has to go somewhere else. That's when things get dangerous. Because structures are like teams. If one member suddenly drops out, everyone else has to pick up the slack. Sometimes they can handle it. Sometimes they can't. And when they can't, you get a chain reaction. That's how local damage turns into total collapse. Now let's make this real. Imagine a simple beam, just a horizontal piece holding up a floor. People walk on it, furniture sits on it. Maybe there's a heavy cabinet on one side. All of that creates load. The beam resists that load by bending slightly. A little bending is normal, completely fine. In fact, every structure you've ever been in is moving, just a tiny bit. You don't notice it, but it's happening. Now increase the load. More people, heavier furniture. Maybe something wasn't built exactly right. The beam bends more. Still okay, but there's a limit. Keep pushing and the internal stress inside that beam keeps rising. At some point, the material, steel, concrete, timber, whatever it is, reaches its strength limit. And once that happens, it doesn't politely warn you. It doesn't say, "Hey, I'm about to fail." It just goes. That's the ultimate limit. No more capacity left. Now here's something a lot of people misunderstand. They think structures are designed so that this never ever happens. That's not exactly true. Engineers know that loads can be unpredictable. People might overload a space. Weather can be extreme. Materials are never perfect. So instead of pretending failure is impossible, engineers design with a buffer, a margin, a safety cushion. This is where the idea of a safety factor comes in, and it's one of the most important ideas in engineering. Let's say a beam can theoretically carry 10 tons before it fails. Engineers will not design it to carry 10 tons, not even close. They might only allow it to carry 5 or 6. Why? Because reality is messy. Loads are uncertain. Construction isn't perfect. Materials vary. So that extra capacity, that gap between what it can handle and what it's actually used for, that's what keeps things safe. That's why most buildings don't just collapse out of nowhere. They're designed with breathing room. But, and this is important, that breathing room is not infinite. If you keep pushing a structure beyond what it was designed for, eventually you eat into that safety margin. And once that margin is gone, you're getting dangerously close to the edge. Now let's talk about different ways things can fail. Because collapse isn't just one thing. A steel beam might yield, meaning it deforms permanently before it breaks. Concrete might crack and crush. A slender column might buckle, which is a fancy way of saying it suddenly bends sideways and loses its ability to carry load. Foundations might fail because the soil underneath them can't take the pressure. Different materials, different mechanisms, same outcome. The structure can no longer do its job. Now here's where things get even more serious. Some failures are gradual. You might see warning signs, big deflections, visible cracks getting worse over time, creaking sounds. Other failures are sudden, no warning. Everything looks fine until it isn't. And that's what makes this limit so dangerous. Because once you cross it, there's often no time to react, no second chance. Now let's connect this back to real life. When you hear about buildings collapsing in the news, it's almost always a failure of this kind. Something exceeded its ultimate capacity. Maybe it was overloaded. Maybe there was a design mistake. Maybe materials degraded over time. Maybe maintenance was ignored. But at the core, it's always the same story. A critical element hit its limit, and the structure couldn't recover. That's why engineers are obsessed with this. Every calculation, every design check, every code requirement, this is the first thing they look at. Because if you get this wrong, nothing else matters. Not comfort, not aesthetics, not cost savings, none of it. Now here's a subtle point that separates good engineers from average ones. It's not just about making sure nothing fails. It's about understanding how it would fail if pushed. Because some types of failure are more forgiving than others. For example, a ductile failure, like steel yielding, gives warning. It deforms, it stretches. You might notice something is wrong. A brittle failure, like certain types of concrete crushing, can be sudden and catastrophic. No warning. So engineers don't just want strength, they want controlled behavior, predictable behavior. They want the structure to fail nicely, if that makes sense. Because in extreme situations, that can save lives. Now let me give you one more way to think about this. Imagine you're driving a car. You're well within the speed limit. Everything feels stable. You start going faster. Still okay. Push it further and the car becomes harder to control. At some point, if you push too far, you lose control completely. That loss of control, that's your ultimate limit. And just like driving, the danger isn't just the speed, it's how close you are to the edge without realizing it. So when engineers design a building, they're basically asking, in the worst possible realistic scenario, does this thing still hold together? Not just under normal use, under extreme conditions, heavy loads, strong winds, unexpected situations. And if the answer is yes, with a comfortable margin, then the structure passes this check. If not, it goes back to the drawing board. No compromises. Because this is the line you do not cross. Ever. So now you understand the first limit. The one about survival. The one about whether the structure stands or fails. But here's the twist. Most of the problems you'll actually experience in real life
They don't come from this limit. They come from the other one, the quieter one, the one that doesn't make headlines but drives people crazy. And that's exactly what we're getting into next.
Let's talk about the one people actually feel every day. This one doesn't make the news. No dramatic collapses, no viral videos. But if you've ever lived in a place that just feels off, you've already experienced it. This is what engineers call the serviceability limit state. Again, forget the name. Let's say it in plain English. This is the point where the building is still safe, but it's no longer okay to use. That's it. Nothing is breaking, nothing is collapsing, but something isn't right. And once you notice it, you can't unsee it. Now, let's make this real. Imagine you're in your apartment. Someone walks across the room and you feel the floor move. Not a lot, just enough to notice. At first you think, maybe I'm imagining it. Then it keeps happening. Every step, every movement. Now, technically, the structure is fine. It's not going to collapse. But would you feel comfortable living there? Probably not. That's a serviceability problem. Now, let's go through a few more examples, because this is where it really clicks. Cracks in the wall. You see a thin line running across the plaster, then another one shows up, maybe near the ceiling, maybe around the window. Structurally, it might be completely safe, but psychologically, it bothers you. You start wondering, is something wrong with this building? That uncertainty, that loss of confidence, that's part of the problem. Now, think about doors. A door that used to close perfectly now doesn't. You have to push it harder, or it gets stuck, or it swings open by itself. That's not dangerous, but it tells you something has shifted, something has moved. And again, it chips away at your trust in the space. Or take something like vibration. This is a big one in modern buildings, especially with long spans, lighter materials, open-plan designs. You walk and the floor responds. Someone drops something and you feel it through the structure. Gym on the upper floor? Good luck. The building might be 100% safe from collapse, but the experience, terrible. Now, here's the key idea. Serviceability is all about how a structure behaves under normal use, not extreme loads, not rare events, just everyday life. Walking, sitting, opening doors, living. And engineers have to design for that just as carefully as they design for strength, because if they don't, you end up with buildings that are technically fine, but practically unacceptable. Now, here's something that surprises a lot of people. Serviceability problems often show up way earlier than structural ones. Long before anything is close to collapsing, you'll start seeing deflection, things bending more than they should, cracking, materials reacting to stress and movement, vibration, structures being too flexible. These are early signs that you're approaching that second limit. Not the dangerous one, but still a limit. And if you ignore it, the building might never collapse, but it will never feel right either. Now, let's talk about why this happens. Because it's not always about bad design. Sometimes it's actually a trade-off. Remember in the last part we talked about safety margins? Well, if you design everything super stiff, super strong, super solid, you solve a lot of serviceability problems. No movement, no vibration, no cracks. But here's the catch. It becomes expensive, very expensive. More material, heavier structure, higher cost. So engineers are constantly balancing this. They're asking, how much movement is acceptable? How much cracking is okay? How much vibration can people tolerate before they start complaining? And yes, complaining is actually part of the design consideration, because at the end of the day,
Buildings are for people, not just for calculations. Now, here's where things get a bit more human. Serviceability is not just about physics, it's about perception. Two floors can have the exact same amount of movement. One feels fine, the other feels terrible. Why? Because people are sensitive, especially to motion. A tiny vibration that's technically within limits can still make someone uncomfortable. That's why things like office buildings, residential buildings, and hospitals all have different serviceability requirements. Same structure, different expectations. Now, let's clear up a big misunderstanding. Just because you see a crack doesn't mean the building is unsafe. And just because everything looks perfect doesn't mean everything is fine. That's the tricky part. Serviceability lives in that gray area. It's not about life and death. It's about quality, comfort, trust. And once that trust is gone, the building fails in a different way, not structurally, but functionally. Now, here's something engineers always keep in mind. Serviceability problems can turn into structural problems if ignored long enough. For example, a small crack lets water in. Water causes corrosion. Corrosion weakens reinforcement. Over time, what started as a harmless crack becomes a serious issue. So even though serviceability isn't immediately dangerous, it's not something you just ignore. It's an early warning system, a signal. Now, let me give you a simple way to remember all this. If the ultimate limit is about survival, then the serviceability limit is about livability. Can you actually live in this space without being annoyed, uncomfortable, or constantly worried? That's the question. And good design answers yes to both limits, not just one. Because a building that never collapses but feels horrible is still a bad building. So now you've got the full picture. One limit is loud, dramatic, and unforgiving. The other is quiet, subtle, and constant. And every real structure is living somewhere between those two lines. Now, the question is, how do engineers actually balance them? Because pushing too far in one direction always creates problems in the other. And that's where the real design decisions happen.
All right, now we get to the part where real engineering decisions happen. Because up to now, it all sounds simple, right? Two limits. Don't let the building collapse. Make sure it feels okay to use. Sounds obvious. But here's the problem. You can't maximize both at the same time. And this is where things get interesting. Every design is a trade-off. Always. Now imagine this. You tell an engineer, I want this building to feel rock solid. No movement, no vibration, no cracks. Perfect. Can they do it? Yes, absolutely. They can make the structure insanely stiff. Huge beams, thick slabs, massive columns. Over-design everything. You walk inside, feels like a bunker. Nothing moves. Perfect, right? Not really, because now the cost has exploded. Materials, labor, foundation loads, everything goes up. You're paying way more than you need to, and in most real projects, that's not acceptable. Now flip it the other way. You say, I want this as cheap and efficient as possible. Again, engineers can do that. Slim beams, long spans, less material, lower cost. Structurally, it might still be safe, it won't collapse. But now you start getting problems. Floors feel bouncy, vibrations show up more easily, cracks appear more easily. People complain. So what just happened? You stayed safe on the collapse side, but you crossed into problems on the comfort side. That's the balancing act. Every single structure sits somewhere between those two limits, and the engineer's job is to place it in the right spot. Not too conservative, not too risky, just right. Now here's how they actually do that. First, they look at loads. And I don't just mean weight. Loads include everything: people, furniture, equipment, wind, snow, even things like temperature changes. Then, they don't just take one number and design for it. They combine them, because in real life, loads don't happen in isolation. You might have people inside and wind outside, or heavy equipment and vibration. So engineers create what are called load combinations, different scenarios, different what-if situations. Now here's the key. For the ultimate limit, the collapse one, they assume worse conditions, heavier loads, more extreme cases, and they also reduce the assumed strength of materials slightly. Why? Because they're being cautious. They're building in uncertainty. They're asking, what's the worst realistic case, and does this still hold? If yes, good. If not, redesign. Now for serviceability, the approach is different. Because here, it's not about extreme situations. It's about everyday use. So the loads are more realistic, not exaggerated. And the focus shifts. Instead of asking, will it break? They ask, how much will it move? How much will it bend? Will people notice? That's why you'll often hear engineers talk about things like deflection limits, vibration criteria, crack width control. These are not about safety, they're about experience. Now here's something subtle but very important. A design that passes the ultimate limit check does not automatically pass the serviceability check, and this catches a lot of people off guard, because you might think if it's strong enough, it should be fine. Not true. A structure can be strong, but flexible. It won't break, but it might move too much, and that movement is what people feel. So engineers have to check both, separately, every time. Now let's talk about priorities. If there's ever a conflict, and there often is, the ultimate limit always wins. Always. Safety comes first, no negotiation. But that doesn't mean serviceability is optional, because if you ignore it, the building might be safe, but it becomes a problem in a different way. People complain, tenants leave, maintenance costs go up, reputation gets damaged. In some cases, you even have to retrofit or strengthen the structure later, which is way more expensive than doing it right the first time. So smart design is not about pushing everything to the maximum. It's about understanding where you are relative to both limits and staying comfortably within both. Now here's the part that separates good engineers from great ones. Good engineers follow the rules. They check the boxes. They meet the requirements. Great engineers understand behavior. They can look at a design and feel where the problems might show up. They know when something is technically acceptable, but practically risky, and they adjust before it becomes an issue. Because in the real world, it's not just about passing calculations. It's about how the building actually performs once people start using it. Now let me give you a simple way to picture this. Imagine a line. On one end, you have collapse. That's the ultimate limit. On the other, you have perfect stiffness, zero movement, maximum comfort. Somewhere in between is the sweet spot. Safe, efficient, comfortable enough. That's where every good design aims to land. Too far towards safety, you waste money. Too far towards efficiency, you annoy people. Too far in either direction, you failed in some way. And the tricky part, that perfect zone is not fixed. It changes depending on the building. A hospital needs stricter control because people are sensitive. Equipment is precise. An office building might allow a bit more movement. A warehouse, even more. Different use, different expectations. Same two limits, different balance. So when you look at a building, you're not just looking at concrete and steel. You're looking at a set of decisions, trade-offs, judgments, all centered around one simple idea. Stay away from collapse and don't make life miserable for the people inside. That's the real job. And once you understand that, you start to see buildings very differently, not as static objects, but as systems carefully tuned to live between two invisible lines. And getting that balance right, that's what engineering is really about.
Let's bring this back to real life, because everything we've talked about so far sounds clean, logical, controlled. Two limits. Engineers calculate everything.
Stay within the lines and you're good. But in the real world, people misunderstand buildings all the time. They either panic over the wrong things or ignore the ones that actually matter. So let's clear that up. Here are some of the most common misconceptions, and once you see them, you'll start noticing them everywhere. First one, if it hasn't collapsed, it must be safe. This is probably the biggest mistake people make. A structure doesn't go from perfectly fine to collapsed overnight. There's a whole process in between. Damage accumulates, materials weaken, loads change, and sometimes a structure can be much closer to its limit than it looks. Just because it's still standing doesn't mean it's comfortably safe. It might be right on the edge. And the scary part? You often can't see that edge. Second, cracks mean the building is dangerous. Not necessarily. This one goes the other way. People panic too quickly. Most cracks you see in walls, especially small, thin ones in plaster, are serviceability issues. They're about movement, shrinkage, temperature changes. They look bad, sure, but structurally, they're often harmless. Now, that doesn't mean all cracks are safe. Wide cracks, growing cracks, cracks in structural elements, those are a different story. But the key point is this: a crack is a signal, not a conclusion. You have to understand what kind of signal it is. Third, if it feels shaky, it's about to collapse. This one is super common, especially in modern buildings. You feel vibration and your brain immediately goes, "This is not safe." But in many cases, that vibration is a serviceability issue. The structure is flexible, not weak. It moves, but within safe limits. Engineers actually allow for this because eliminating all movement would make the building too expensive. So yes, it might feel uncomfortable, but that doesn't automatically mean danger. Still, perception matters. If people don't feel safe, that's a problem in itself. Fourth, if it looks perfect, everything must be fine. This one is the most dangerous of all because structural problems don't always show up on the surface. A beam can be overstressed, a connection can be weakening, reinforcement inside concrete can be corroding, and from the outside, everything looks clean. Fresh paint, no cracks, no visible signs. That's why inspections, maintenance, and proper design matter so much, because you can't rely on appearances, not with structures. Now here's the bigger picture. All these misunderstandings come from the same place. People don't know the difference between the two limits. They don't know if what they're seeing is about comfort or safety. So they either overreact or they ignore something serious, and both can be dangerous in different ways. Now let's flip this into something useful. How should you actually think about buildings? Here's a simple way to break it down. If something is annoying, but stable, not getting worse, and not affecting structural elements, it's probably a serviceability issue. Uncomfortable, frustrating, but not immediately dangerous. If something is changing, getting worse over time, spreading, affecting key parts of the structure, that's when you pay attention, because now you might be moving toward the ultimate limit, and that's not something you guess about. That's when professionals step in. Now here's one last idea I want to leave you with. The most dangerous structures are not always the ones that look bad. They're the ones where the limits are misunderstood, where people assume everything is fine until it isn't. Because unlike serviceability problems, which annoy you every day, ultimate failure doesn't give you many chances. When that line is crossed, it's often sudden and irreversible. So engineers don't design for probably fine. They design for definitely safe, with margin, with caution, with respect for those limits. And once you understand that, you start to see buildings differently. Not just as walls and floors, but as systems constantly balancing between two invisible boundaries. One you feel every day, and one you never want to experience. And that's really the whole story. Every structure you walk into is quietly sitting between those two lines, held there by design, calculation, and a lot of decisions you'll never see, until something goes wrong, and by then, it's already too late.